Okay, great. So now we need to, it's like a small recap of the previous lecture. And now we need to speak a little bit about the rigid body dynamics. So if we if we'll consider just a rigid body, we can write down the following. It's like if we have a point mass, the kinetic energy will be just 1/2 mass v squared. But this is in the case if v is a scalar. If v is a vector, you need to multiply v transpose times v. And it's just only one component when you do have the motion, like translation without rotation. Okay. But still, it has some, it's like we have 1/2 mass and the linear velocity. The full kinetic energy will look like this. And we are familiar with this thing. But how can we derive the equation using linear algebra? We do know that the kinetic energy of a robot is just the sum of links, right? So if you just do the summation, the adding of different links, you can compute the kinetic energy of the whole system. But if we'll consider not a robot that consists of several links, but a rigid body, so we can assume that we have like this kind of rigid body with a complex shape. It's not a brick, it's some kind of robot part which is complex. How can we compute the kinetic energy of this rigid body? Let's assume for now not the whole volume, but very small piece of this component, which is called infinitesimal mass. It's like a very tiny piece of body. How can we compute the kinetic energy of this component, this portion? We can do pretty much the same, that it will be 1/2. But now we can think about the mass as the multiplication of density, rho, with the volume. So this will be the mass, this tiny piece of mass. And we need to multiply it with the velocity, with this portion, right? So we do understand how can we express position, the p, this one. So we know how to do this. And we do understand that the p dot, for example, equal to twist in matrix form times p. So we do understand how to do the p dot. So here we can put p dot transpose p dot, and it will be the same as v squared. Do you agree? So this will be the following. It is analogous. Do you agree?
It's like v transpose. It's like v transpose times v.
Yeah. Yeah. And we already know how to compute it from the kinematics. All right. So it's like the tiny piece, and the kinetic energy of this part will be the following. So you can see that rho is not a constant, but it's a function, and it depends on p. So it's not like rho times p, but rho depends on p, because when you have a link of a robot, it is not homogeneous, right? It's like you have a shell, a metal shell, you have some kind of gearbox with an actuator, you have some hollow parts in it, so the density is not homogeneous. It's like in your simulation model, it could be, but in real life, it is not, and this is why it is actually a function. It is important that it's not a constant. I will explain you in a minute. So is it clear for now? Okay. So since we do understand the kinetic energy of this tiny piece, we can take an integral of entire volume, and it will be the kinetic energy of entire rigid body. Okay? So just integral of this will be the kinetic energy of the whole body. Okay. We do understand that if something is constant, we can take it from the integral sign. For example, 1/2 we can take from integral sign. What else? Density is not constant. I just told you that it is not constant. And for this reason, we cannot take it from the integral sign. What is about the p dot? No, it's still not constant. So basically, just 1/2, right? But we still want to do some kind of simplification. And maybe you do remember that somehow we can express velocity such that it will be constant for entire body. What it will be? Angular velocity, definitely. What else? Twist. Exactly. We just derived that the twist will be constant for all points. And if we will do something like here, we will have not a p dot, but something with a twist. In this case, we can take the twist out of the integral sign. So basically, we'll try to do the following. All right. We have this kind of expression, and let me just write an expression for the same motion, but expressed in the B frame. So basically, it will be the same, but like this. So from here, so what do you have here on slide? So I have here like this, equal to the HOI twist IOI. So it is exactly this thing, I guess. No, opposite. So yeah, it is for a twist that expressed in the body frame. Here the twist expressed in the A frame. So from here, it's like that case. From here I can derive H dot AB, which equal to this twist BAB. If I want to derive H dot, I need to multiply both sides on the inverse of this h. So it's like here I need to put h BA, and here it will be h BA. So here I need to put BA, and it's just like here. Dot A B B B. P, for example, A equal to H A B P B, and if we'll take a time derivative of that, it will be P A equal to H A B dot P B. Do you agree? It's like if PB, if the distance, if we'll consider the rigid body, the distance P will be constant and the derivative of PB will be just 0. So instead of this thing, we put this thing, and this is how we can get the expression that PA equal to H A B twist tilde B A B P B. Do you agree? Okay. So now instead of H, we can put this equation. Instead of twist, we can write the expression for the twist, where we have the skew-symmetric representation for angular velocity V 0, 0, and P. Here you have a P capital, so P capital it equals to the P with a 1, so it's a column of 4 entities. So now you can. I hope that you do understand this expression. And if we'll do the multiplication, we will be left with this component. P dot will be equal to this term plus this term. Do you agree? And it will be nothing else as something that we are going to put here. So here you can see the derivation. So we just derived that P dot equal to the R times the angular velocity in skew-symmetric form times P, the position, plus R times the linear component. So the sum of them so here we can take the R. This is the R. We have angular velocity in skew-symmetric form times P plus linear velocity. What does it mean, skew-symmetric representation? It's a way how can we do the vector product, right? So we can rewrite it in this form. And we can do this trick. We can change the places. And in this case, you need to put a minus. And we can rewrite such that now the position vector will be in the skew-symmetric form. So if we'll do the derivation, we will get the expression when we can take the angular velocity and linear velocity as a vector, and it will be nothing else as a twist in vector form here, because angular velocity is not skew-symmetric representation. Do you see that? Okay. So, and it will be the p dot, and we need p dot transpose. So p dot transpose will be, so what do we have? We have some component times twist, right? And all this need to be transposed, okay? So when we do the transpose, we need to switch places, yeah? And it will be then twist transpose and this brackets transpose. So if we'll do the transpose of this minus rp in tilde with the tilde r, we will have the following. So I will just continue here. I need more. So. So if I want to take the transpose of that, it used to be a row, now it will be a column. So it will be minus r0 p square, and all of this transpose. RIO will be transposed, and we need just to switch the indices, so it will be RIO. Okay? So here also we need to switch places. It will be minus P tilde transpose RIO. RIO. And because it's skew-symmetric, we do understand that skew-symmetric means that it equals transpose itself transpose. So instead of this, we can just put like this. Okay? Since it's skew-symmetric form. So what we'll have here, actually, it will be instead of this, it will be twist transpose P tilde RIO times this part minus ROI P I ROI twist. Do you agree? And those twists, we can take those out of the integral sign. So basically, this is the derivation, the same. So here, this is the skew-symmetric form. So this is the transpose part, not transpose part. And we just took this part. We multiplied with the rho and with the dv, and we call it dm. It's like, actually now it will be the mass matrix for this tiny component. And now we can take the integral, and the integral of this portion will be nothing else as the tensor of inertia. So if we'll do the integration, it will look like this. And if we'll do the correct choice of the frame, and it will be we'll choose the center of mass. If we'll do the right thing, we'll have only components on the main diagonal, and we'll have the components for the moment of inertia. So in a tensor inertia, it will be 6 by 6 matrix, 3 of them for the angular moment of inertia, and m just mass multiplied with the 3 by 3 identity matrix. It will be just m. So this is the inertia, and if we do understand our inertia, we can compute the kinetic energy very easy. 1/2 twist in tensor of inertia times twist. So twist transpose, inertia, twist. But since also we need to express the inertia in this principal frame, such as we have components only for the main diagonal, we also need to have here a joint. A joint we use when we want to do the to express the twist in some kind of another frame, and here it will be principal frame, principal inertia frame. So if we'll do the multiplication, we'll find out that actually it equal to the I already erased it, 1/2 times m times v in power 2, and all the components for angular velocity for all the moment of inertia. So basically, when you have a rigid body, you need to put all the components. In our example, at the third lecture, I had a point mass in my example. But for a rigid body, we actually need to put all of them. Okay. So we do now understand how to compute kinetic energy. But how can we model a body, for example, using bone graphs? We do understand that the multiplication of mass times velocity for a point mass will be momenta. Pretty much the same is true for the spatial motion. In this case, we need to multiply the tensor of inertia times twist, and it will be the momentum in screw theory. But here we can see that is expressed. So it will take the multiplication of this momenta. It will be force, so it will be range, but it is expressed in inertia frame, not in the body frame, but inertia frame. So momenta in inertia frame is equal to the range. If we express the momenta not in the inertia frame but in body frame, in this case we need to use the adjoint, right? So if we want to switch the frames, we need to use a adjoint. So in the body frame, it will be like we need to take the derivative of the adjoint, and if we'll do this, so basically we need to take the time derivative of the adjoint. All the multiplication I have right here, So the multiplication of adjoint will be just another matrix here. It's not really important how it looks like. We just need to understand that we're able to take the derivative of adjoint, and if we'll continue our derivation, we'll find out that the range, this range, actually equal to the sum of these two components. It's like when we, if we will express it in the inertia frame, there is only one component, just p dot. But now here we have two components. If we'll just do the whole derivation, we'll find out that p dot equal to the range times additional term, and this additional term is nothing else as the horoscopic effect. I mentioned it at the very first lecture. And if we multiply each component, so those are the equation of forces, and if you multiply each component on the twist, it will be the equation for the power. So here, equation for the momenta. If we multiply each part on the twist, it will be p dot twist equal to the term of the gyroscopic effect times twist plus range times t twist. And the range times twist, actually it's the amount of power that we send it as an input on a body. So if I will just so here I'm applying the range, right? I'm applying range to this bottle, and this bottle saves energy, and this energy is nothing else as a p dot times twist. And the second term is the gyroscopic effect that force a body to flip. That one. So the flip, the reason of this flip is this second term, and we can find it if we'll do the derivation correctly. So now let us proceed to the Euler-Lagrange equation. How much time do we have? We have started. I guess now it's break time. Yeah, sure. We'll continue after the break.